So what we have done so far as far as detonation is concerned is to come up with a way by which we can get the detonation wave velocity, for which we realize that we don't necessarily have to get into the wave structure, unlike what we did for the deflagrations. But in any case it's also important for us to actually think a little bit about the detonation wave structure if you want to get into applications with detonation waves, as we pointed out, for example in pulse detonation engines, which is coming up as a good alternative to engines that are commonly used now. So today we will just look at detonation wave structure. Now in reality a detonation wave is highly three dimensional. The structure is very complicated, but just for the sake of simplicity we could still adopt a one dimensional approach by which we now try to see what happens within the detonation wave, just like how we did for the deflagration wave, where we said we look at a planar deflagration and you have upstream heat conduction and reaction rates towards the later downstream part of the flame thickness and so on. Similarly we can have a similar approach, and the first kind of advancement that was done in this is what is typically called as the ZND model, which stands for Zeldovich. As usual, as with most things in combustion, it always has to have Zeldovich there. So this actually stands for Zeldovich, Neumann and Düring, who independently, all three of them independently evolved this idea in the time frame of about 1940 to 1942. That's around the time frame. Of course there is a historical perspective about this. Detonations are something that is somewhat destructive most of the time, and this time frame that we are talking about was also the time of the Second World War, so there was good reason to expect why people should be working on this at that time. So the basic idea of the ZND model is one of shock followed by chemical reactions. That is to say, a detonation wave is nothing but starting with the shock followed by chemical reaction. So keep in mind, detonation waves propagate at supersonic speeds, so do normal shocks. So we are talking about a normal shock propagation, and the job of the normal shock is, as far as the detonation wave is concerned, with respect to this model, is to increase the temperature downstream of the shock to a high enough level that will now get the reactions going at as fast rates as is required for the reaction zone to follow the shock, right. So previously in the case of deflagrations, if you now let the reaction rates happen by themselves, then the propagation rate is limited by how fast the heat release from the chemical reactions can get conducted upstream to the reactants, whereas here we don't have that problem. In fact, the problem here is, can we have the chemical reactions happen fast enough to be able for that layer of chemical reactions to closely follow the shock. So effectively then the entire detonation wave is all about the shock rising the temperature of the downstream gas, still reactants as a matter of fact, because you don't expect too much reaction to happen within the shock, because the normal shock is only a few mean free paths thick. That kind of thickness is not sufficient for significant amount of collisions to happen between the reactants for appreciable reactions to happen. Therefore you are essentially rising the temperature of the reactants to a high enough level such that the reaction rates are appreciable, and then this reaction layer will faithfully follow the shock. This is essentially the approximation. We will see how this approximation can be relaxed as we discuss this a little bit further, but within the framework of the ZND model, the essential approximation is the first thing that you have is a shock, and then you have chemical reactions. So the normal shock in the reactant mixture rises the temperature to such level as to cause significant reaction rates for reaction zone to follow the shock. So in fact what typically happens is, so if you now think about how to look at what happens within a detonation wave, let us suppose now you consider the thickness of a detonation wave. The first thing that we are looking at is like a shock that happens right here, which is very, very thin, and then so if you now look at how the temperature varies, so you now start with a T naught, and then across the shock the temperature actually increases to jumps to a value, but that is not the end of the story, right? Because in reality now if you have chemical reactions you have to reach something like the flame temperature, and the shock itself is not going to rise the temperature up to the flame temperature, it's going to rise it up to some point, and then subsequently you now have a region where the temperature remains constant for some distance, and then it begins to increase very similar to the way it increases in the deflagration wave pattern, and then levels off. So this is for example your T infinity there, starting from T naught, and this temperature this value that the temperature rises to just downstream of the shock is sufficiently high enough for chemical reactions to happen in this region. So of course in this picture we can try to alter so in this picture we now have a region that's where the temperature levels off just after the shock, which we will now call the induction zone, and this is the reaction zone. So the induction zone is where you have the reactants are now elevated to a temperature and then go through a induction period. Keep in mind this is not a very long period because the entire flow is happening very fast, right? So you have a short induction period when the reactants begin to sense the temperature and then cause reactions that will cause additional further increase in temperature. So this is the time when the reaction rates are just barely beginning to build up because you have the exponential dependence on temperature, right? And then it shoots up. So you have this induction zone where you have nearly more or less a constant temperature, and then you have this sudden rise. This rise, unlike in deflagrations, is having a significant convective effect along. In the case of deflagrations we had a preheat zone which was primarily containing a conductive diffusive balance with no reactive component, and then the reaction zone where you had a reactive diffusive balance with hardly a convective effect. But here you have significant convection happening in this reaction zone as well because you have very high, very fast flow rates there. So if you now think about this kind of a situation for the temperature, correspondingly if you now look at the pressure, right? So if you think about the pressure, and then let us suppose that you start with the same line for P naught as well. The P naught, of course we are normalizing things, right? So the P naught actually goes up to a significantly high value, and then think about what happens when you have chemical reactions. You have a pressure that decreases, right? So you actually go through a decrease in the pressure through the through the reactions. So you reach a pressure that is higher than what you actually see outside of the detonation wave. So you think that you got a very high pressure behind the detonation wave, and this is the jump that you are beginning to talk about, alright. But in reality you went through a fairly further increase in pressure. We will begin to talk about that pretty soon, okay. That is because in the shock you have a pressure rise, and then you have a chemical reaction similar to the deflagration where you have a pressure decrease, alright. Now you can say, okay, this rise is a lot more when compared to this decrease. All that stuff is correct. So you can quantify this to find out that you don't have a big difference between these two. In any case you have a pressure rise and followed by a decay. That's the important thing that you have to think about. Similarly, can we now think about the velocity, right. So across a normal shock the velocity decreases, right, and then we are talking about a Chapman-Jouguet detonation wave for most part. In any case in all these detonations we found that the reactants follow the wave, sorry, the products follow the wave at a velocity that is or at a Mach number that is lower than the incoming Mach number, right. So you have to end up with a lower velocity than you start out with. That means you start with a high velocity, that's your u0, and then this decreases significantly across the shock. And what happens when you have a flow going through a deflagration situation where you have a temperature rise, then the density falls and therefore the velocity increases, right. So you now have a velocity increase that happens over here, so you get a u infinity. So the velocity drop that you sense across the detonation wave in a Rankine-Hugoniot framework is actually this, but in reality if you go into the wave you find that the velocity drop is even further down before it actually restores to a level that is higher than here but lower than there. So these are the kinds of things that are going on similar. But then of course if you now think about reactant concentration, right. So if you now look at reactant concentration, you started out with a high reactant level, so let us say YR, but no change across the shock, right. So the reactant concentrations are pretty much remaining the same and begin to decay only maybe you can look at the deficient reactant, go all the way down to 0 over here or fairly low value. So you say you can say YR naught and then YR infinity, right. So this variation happens only in the reaction zone, it does not happen before that. So you begin to understand these kinds of things. So can we now think about how the state of the gases move through the reaction, so the detonation wave thickness within a Rankine-Hugoniot framework, right. So if I want to now do that, let me then plot my Hugoniot plot where you have P infinity and then 1 over rho infinity is what is classically plotted, but I am going to actually track the state of the system before it reaches P infinity. That means my P infinity as I go along x, whatever is my P I'm going to try to track. So from the origin which is your P naught 1 over rho naught, right, and the Hugoniot curve goes like that. And what does the ZND model say? It says shock followed by chemical reactions. This offset for the Hugoniot curve is essentially coming from the fact that you have a heat release, okay. The heat release is going to push the Hugoniot, more and more heat release in the wave is going to push the Hugoniot to the top and to the right. So when you are now looking at how a shock is going to be represented, that is a adiabatic process. That means you do not have any heat release across the shock itself, right. The heat release comes behind, therefore you have to follow the shock Hugoniot. So the shock Hugoniot is now going to be passing through the origin, So that is the shock Hugoniot. And we are looking at the Chapman-Jouguet wave, so that is the UCJ point, and that means you are looking at a tangent Rayleigh line to the actual Hugoniot with the full heat release, but then we are looking for how you are trying to locate your point between successive Rayleigh lines intersecting successive Hugoniot curves for different q. That means as we go along from here to there, you are having heat release happening, and then the velocity gradient also keeps changing. So what we want to do is look at a Rayleigh line with viscous effects, alright. So the viscous effects will now bring in the velocity gradient into it. So integrating the momentum equation in steady 1D framework, we have done this twice so far within. So here what we are talking about is within the detonation wave, we can now get P infinity minus P naught equals minus m dot squared 1 over rho infinity minus 1 over rho naught plus 4 by 3 mu du by dx. So of course you can now fix your x going this way, right. When did we get this before? When we wanted to show that when you have very low Mach number, this will actually be of the order of Knudsen number times Mach number, and then the convective term will actually be of the order of gamma times Mach number squared, and so under very low Mach number conditions for continuum flows with low Knudsen numbers, you got a pressure equal to constant approximately. That is when we tried to integrate it once. The next time we integrated it was in the Rankine-Hugoniot framework, but that is like saying all the gradients are within the wave. That means we are looking at outside the wave to get jump conditions, so you don't have the du by dx term at all, right. So now we have a du by dx term kept in order to see what happens when you now traverse through this wave, right. So if you do this, then what we find is you now have a decrease in u with increase in x. So you start with negative du by dx, and then you begin to have and then you go to 0 du by dx, and then you have a positive du by dx, and then again you go back to 0 du by dx. Okay. So if you have a 0 du by dx, then you get back to the Rayleigh line that you are familiar with, alright, and that is the Rayleigh line that we have plotted here. So you start from here, right, that is for 0 du by dx, you go through a 0 du by dx again, and you go through a 0 du by dx again. So you go through this 3 times, once at the start, once at the end, and once somewhere in between, alright. That means our system should actually the system should actually lie on the original Rayleigh line 3 times, starting at this point, ending at this point, alright, but also somewhere in between. Okay. So how do I represent this curve? This is basically again a straight line with the same slope minus m dot squared, right, but now having an intercept. So if I have negative du by dx, maybe I can use a different color chalk piece. I can now think about several Rayleigh lines that are parallel to this, like this, and these are with negative du by dx, and if I want to go positive I have to draw lines that are like that, and these are lines with positive du by dx. So the original Rayleigh line now begins to look like that corresponding to 0 du by dx, right. Okay, so if you strictly follow the idea of having a shock followed by reactions and the heat release is happening only in the reactions, what it basically means is you rapidly go from the origin through a negative set of du by dx lines, okay, through a set of negative du by dx Rayleigh lines along the shock Hugoniot, right, as rapidly as you can, go up to the peak pressure, and I told you I'll talk about this, right. So you go up to the peak pressure all the way and then start turning around when you now get this du by dx to flatten out to 0 back again, right. So the positive du by dx begins to decrease back to 0. That means your path would now go along the shock Hugoniot as much as possible. You see the moment the shock Hugoniot is deviating from the Rayleigh line like in tangent Rayleigh with a positive with a negative du by dx, your du by dx is now beginning to grow, right, back to 0, and then that means it now begins to go away from there and reaches your 0 du by dx, and then you have to go through the positive du by dx region, right, when the pressure begins to fall again. Therefore you now reach the situation where you got this peak and then you go through positive du by dx lines and then come back to this, come back to the 0 du by dx Rayleigh line, right. So this basically means that you are now going to have a peak that is called the von Neumann spike. Slower and slower the chemical reactions, you have the delay in the chemical reactions, so you have a shock that first happens to increase the pressure, right, then you get to follow more and more of this path. If your chemical reactions are a bit faster, if you can try to actually get the chemical reactions to be faster, you could hope for other paths, maybe use a couple of other color chalk pieces here, you could use other paths. Our destination is from here to there, right, so you could either go like this or like this, but usually this one, the blue line, requires ultra fast reactions. That means you are very much farther away from the shock Hugoniot, right, you are beginning to think about reactions happening even within the initial layer itself as the increase in pressures are happening, so you don't really go all the way to the von Neumann spike at all, right. Whereas if you had modestly reacting mixtures, you could still go through a pressure that is higher than the Chapin-Jouguet downstream pressure, right, and that would lead to something like a von Neumann spike. But the worst case von Neumann spike that you can get is when you're thinking about the ZND model, where you're saying all you have is a shock to begin with and then you have chemical reactions following that, alright. So this is a way by which you can compute the von Neumann spike and get the worst case pressure or worst case or best case depending upon what your goal is. So if you want to have your detonation wave inside a chamber and you want the chamber to withstand the pressure, this is the worst case pressure, but if you want to cause destruction by pressure by having a very high pressure region, then this is the best case pressure for you, right. So this is the extreme pressure that you can think about with in the framework of the ZND model. I think we should stop saying anything more within the one dimensional framework, and I'm not going to cover the 3-dimensional details because it's too complicated for this course.